Wait a second, ma'am. Yes. Okay. So, to all the participants, good morning to all of you. And our person for the first session of the day is with us, Professor Kanupriya Sachdev from MNIT Jaipur. So, before starting the session, let me give a brief introduction about her to all of you. Professor Kanupriya Sachdev has done her MSc, MPhil, and PhD from the University of Rajasthan, Jaipur. She joined as lecturer in MNIT Jaipur in the year 1995 and presently working as professor in Department of Physics and Materials Research Center at MNIT Jaipur. She has published more than 100 research articles in reputed journals and the conferences. She has completed 3 research projects granted by the DAE, DRNS, DST, GITA, and IUAC New Delhi. She is a life member of Materials Research Society of India, Indian National Society for Disordered Materials, Science Society of India, Indian Association of Physics Teachers, Executive Committee member, and the life member of the Thermophysical Society of India, Iron Beam Society of India. Her research interests are material science and technology, condensed matter physics, transparent conducting thin films, gas sensing, thermoelectric materials for energy conversion, graphene and its composites for the various applications. So I heartily welcome you, ma'am, in this ATAL FDP on the recent advances in nanoscience and nanotechnology. Thank you for accepting the invitation. And the mic is over to you for the session.
Thank you, Dr. Sanju. And before I start, I just wanted to give a background of the research work which we are doing at MNIT, my group especially. So I have a group of about 8 PhD scholars who are working with me. And in this group, it's a heterogeneous group. A few of them are working on thermoelectric materials. And recently, we have started, although we were working in carbon nanomaterials for a few years back, but recently we have started using these carbon nanomaterials for energy applications, basically the electrochemical energy storage. And this gives me a certain background of where I can talk about this area. And as the program is about the recent advances in nanoscience and nanotechnology. So my lecture will pertain to the carbon nanomaterials. Although there is a variety of carbon nanomaterials which exist, so I'll be talking about a few which we are working on in our research lab. So the outline of my, I hope this my voice is audible and the screen is clearly visible.
Yes, yes, ma'am.
Okay, thank you. So my lecture, the outline of the lecture says that we will just have a brief introduction to nanomaterials, although you must are already familiar with all these things, and then particularly carbon nanomaterials. So we'll be talking about graphene and carbon quantum dots, which find a variety of application. And the graphene, which is the CVD grown graphene, and then RGO, GO and RGO, which we mostly synthesize using the wet chemical method. And what is the advantage of doping? What new functionalities does it introduce there? And how these doped graphene is a better functional material for energy storage and electronics. So this is just a preview of what we are going to talk in this lecture. I hope you find this lecture useful for yourself to get further information about carbon nanomaterials, adding some information to already you know, and it could also give you some idea to carry your research work or take it further in this area. So the carbon nanomaterials, they have large functionalities because of their extensive good properties. These carbon nanomaterials are used in energy. So what are the advantages? They are nanoscale structure, high surface area, and good ion adsorption on these materials with catalysis support. Lithium ion battery is a very, it's a kind of example which everyone knows. And fuel cell, incapacitor, all these devices, energy storage devices, we make use of the carbon nanomaterials. Electronics, the advantages are they provide you with high current density, high electron mobility, high thermal conductivity, and the properties are semiconducting, on the verge of being metallic, and of course, they give you an exceptional property, which is like they are transparent and conducting at the same time. And this is very much useful for the displays, and this conductive transparent thin film finds lots of applications in all these areas. Nanotechnology, the scanning probe microscope, the electron microscope, the nanostructure is analyzed by using these equipment of these materials. In biotechnology, the strong adsorption, high surface area, high affinity, these are the advantages which makes them useful in biotechnology. Materials coming out of this, and actually carbon nanomaterials are very useful also because of there is a large number of composites which you can make out of them. So you can do some metal decoration there. You can make a composite of the different allotropes of carbon. You can mix them with polymer, and all these combinations gives you materials which are lightweight. They have high physical strength, high electronic conductivity, high wear resistance, and this is what makes them good materials in various applications. Now, let us just have a quick look at that what are nanomaterials and what makes them special. So any material which has at least one dimension less than approximately 100 nanometer will be a nanoscale material. And at this scale, what happens is that the properties, the optical, magnetic, electrical, these properties become unique. So they become different from the properties exhibited at the macro scale. And these emergent properties, they have the potential to have a great impact in electronics, medicine, and other fields. So it is possible that if the significant dimension, if it is at nanoscale in all three dimensions, you get a zero-dimensional material. If the significant dimension is only existing in one dimension, then you get nanotubes, fibers, or rods. We call them one-dimensional material. And if two dimensions are significant, we get films and coatings. And of course, it becomes a three-dimensional material if all the three are significant. So this is how we classify them. And the property, the parameter which is highly modified when you go from the three dimension to the lower dimensions, that is the density of states. So density of states gives you an idea that what is the number of energy states which are available to the charge carriers. Okay, whether it's electrons or holes doesn't matter, but the number of energy states which are available to the charge carriers, that modifies drastically when we go to low dimensions. And this gives you the plot. So when we look at this, this is density of states versus energy for a three-dimensional material. You can see it is a continuous graph. And for two dimension, 1 dimension and 0 dimension, that continuity, it becomes a step function in the case of 2 dimension, which is quantum well. And then there are discontinuities introduced in case of 1D and 0D. And of course, you can see that the number of density of states also reduces. So this is the modification in the density of states by reduction in dimensionality, which is responsible for the modification of the electronic properties of the material, thereby affecting the other properties as well. The electronic states, thereby affecting the other properties. When we come to the carbon nanomaterial, carbon has a great ability to polymerize at the atomic level. And it gives you allotropes. So allotropes are the different forms of carbon according to the geometrical structure. So these are called as allotropes or the allotropic modifications. Because of having 4 electrons in the outer layer structure, it gives you a valency of 4, and it can be linked via the single, double or triple covalent bonds also with other elements. And that gives them the great functionality which it provides. You can see in these pictures that this is fullerene, which is a 0-dimensional carbon nanomaterial, also called as buckyball. If you have a single layer, a mono layer of carbon atoms, we call it a graphene. If this single mono layer is rolled, it becomes a carbon nanotube, the 1-dimensional form. And if we have a large number of monolayers staked over each other, we get graphite. This shows the bonding of carbon nanomaterials. This is a very typical Dirac cone structure of graphene. What you see here, that this 2 Dirac cones, they are meeting at a point and there is no band gap. So that gives a semi-metallic character to graphene. And of course, it is possible to tune this and introduce by a very small band gap, and thus make it semiconducting. So you can tune it to change its property and then make it more useful. The pi and the sigma bond, the pi bond in the vertical plane, sigma in the horizontal plane, gives them either sp2 or the sp3 bonding. So different allotropes will have different types of bondings. And if, as I said earlier, the significant dimensions are reduced in all 3 dimensions, then in that case, we get the quantum dots or the nanodots. These nanodots are called carbon quantum dots or graphene quantum dots. So the carbon quantum dots, we have please mute yourself. There's a disturbance in the background.
Yes, ma'am, I'm muting all. Wait a second. When you unmute yourself, because I pressed mute all button. Wait a second, ma'am.
Okay, can you hear me now?
Yes, yes.
Okay, so I was just saying that the carbon quantum dots, they exhibit wavelength dependent fluorescence, okay? And this fluorescence depends on their size. So you can control, you can tune the photoluminescence from deep ultraviolet to visible to NIR just by controlling their size. And they have a large scope in functionalization for any specific application. There are a large number of methods which are used for the synthesis of carbon quantum dots. It could be hydrothermal, solvothermal. You can use electric arc discharge, laser ablation, electrochemical etching, or microwave assisted synthesis. So we can use both the top to bottom as well as bottom up approaches for synthesizing the carbon quantum dots. Similarly, the graphene quantum dots, here also you have many methods are available. And these graphene quantum dots with controlled structures, they can be incorporated into various applications of electronics, optoelectronics, and biosensors. So these shows, the figure shows you a top-down approach where we use a Hammers method. We take graphite, three-dimensional graphite, and then exfoliating it, you get graphene quantum dots. This is graphene nanoparticles exfoliated to get quantum dots, or you can use a bottom-up approach using citric acid and paralyzing it to get the, and then further carbonization will give you graphene quantum dots. All these methods are well established, given in literature, and this is basic, you can say, the using the modified Hammers method. You must be knowing that Hammers method and the modified Hammers method are the two main approaches which are used to synthesize GEO and RGO. Okay, and then from there only we get the graphene quantum dots. So we first have to, use some oxidizing agent to convert graphite into graphene oxide. And this graphene oxide, where many oxygen functional groups are attached, this is now subjected to some reducing agent. Although till now hydrazine hydrate was the most used reducing agent because of its high efficiency, but because of its toxicity, people are looking for various other options, and they are looking for green options also. The only thing is that you need a good reducing agent so that you get a better efficiency out of that, and then hydrothermal and the further processing will give you graphene quantum dots. These are the solution. We could not filter them because of we didn't have the right membrane. So this is a solution of the graphene quantum dot under visible light. This gives you the graphene quantum dot in a UV chamber. And these graphene quantum dots were then analyzed by the transmission electron microscope. And you can see that the size of these graphene quantum dots is less than 10 nanometer. And a very good crystalline behavior is seen in the SAD pattern in this inset. So these graphene quantum dots find lots of applications: photocatalysis, biomonitoring, drug delivery, gene delivery, optical sources, water splitting, electrochemiluminescence, chemiluminescence, LEDs, and photovoltaics, solar cells. If we compare the two, the carbon quantum dots and the graphene quantum dots, then the similarities are that they both are 0D nanoscale dimension materials. And the surface modification is the primary factor which affects the luminescence wavelength of these quantum dots. The main distinction could be there in terms of the overall shape of the nanoparticles. So the carbon quantum dots, they constitute spherical nanoparticles, while the graphene, although there is a dispute in that, Some people say they are the same. There is no difference between them. The graphene quantum dots are believed to adopt disk-like structures. Okay. And the graphene quantum dot, very pure, should have only sp2 hybridized carbon atom, whereas there is a combination of both sp2 and sp3 hybridization in carbon quantum dots. Now we move on to another allotrope, which is graphene. And as we just discussed, it's a one atom thick planar layer of sp2 hybridized carbon atom arranged in a hexagonal structure. And it has very unique and remarkable mechanical, thermal, optical, electrical properties. I showed you the band structure earlier. And so that shows that the two Dirac cones, they meet at a point and there is no band gap there. So effectively, it's a zero band gap semiconductor with zero effective mass and very low scattering of charge carriers. And relative temperature independence results in giving a very high carrier mobility to the charge carriers. So theoretically, it is, you can see it is the order of 2 into 10 power 5 centimeter per square per volt second. And that makes these electrons ballistic. So because of its extremely unique and remarkable properties, the graphene finds its application in batteries, supercapacitors, plastics, polymers, structural material, 3D printing, automotives, thermal management, because it has a very high thermal conductivity, rubber and synthetics, lubricants, concrete and cement, magnets, sensors, electronics, semiconductors, water filtration, transparent conducting electrodes, optoelectronics, transistors, pressure sensors, touch screens, photodetector, NEMS, spintronics, Hall effect sensors, optical modulator, barriers, films and coatings, conductive ink, aerospace, energy generation, electrochemical, corrosion resistance, medical applications, waterproof coating, plasmonics and metamaterials, quantum dot composites, piezoelectric effect, sound transducers. So you can see that if you have bulk graphene, you can make use of it. You have a single layer, you can make use of it. You have a multi-layer, you can make use of it. So any form of graphene, it's highly useful. And with all the devices, electronic devices, especially becoming smaller and smaller, the sensors becoming wearable, they're becoming flexible. So advanced materials are required for such special devices and more advanced applications. And this is where the graphene comes into picture. The first time graphene was produced, it was produced using a Scotch tape method, which is the micromechanical exfoliation. The shortcoming of this elementary method is that also is very basic, very elementary. You don't need any, specific or sophisticated device for this. But the problems are it's non-scalable and you get graphene films with small areas and which are uneven. Then you can use arc discharge techniques for production of graphene. Then there is an epitaxial growth on silicon carbide. You can unzip single wall CNTs because, CNT, single wall CNT is just a roll of a cylinder of graphene and you unzip it, you unroll it, you get graphene, single layer. We can use chemical vapor deposition technique and of course, the wet chemistry approach where we do the chemical exfoliation of graphene and then its reduction to produce RG. But you must remember that reduced graphene oxide is not graphene. There will be still, it will not be completely reduced. It will not be single layer. So it cannot be called as graphene. It may be close to graphene, but not graphene. This is the method which we are using to produce the single layer graphene. We have optimized the method where we can control the number of layers using CVD. So optimizing the parameters, we can grow single layer, monolayer, tri-layer, or more than that as per our application or our requirement. Now, generally, the low pressure chemical vapor deposition of graphene is a method where we use a metallic substrate, copper or nickel mostly. And then there is some gas which has carbon, some carbonaceous gas which is used as a precursor. And then argon gas is there as a carrier. And hydrogen is there which serves a double role as an activator for the surface bound carbon and also as an etching reagent which controls the size and morphology during the growth. So there is a typical procedure for the synthesis of CVD graphene. So the metallic substrate, which acts as a catalyst, basically, it has to be heated inside the reactor up to the annealing temperature. And the substrate is annealed at the stabilized temperature with the flow of the reductive gas, the hydrogen. The optimal annealing condition, that means the temperature, the gas composition, the time for which you do it, it has to be optimized so that the metal oxides are effectively reduced, the surface contaminants are removed, and that the metal recrystallization is promoted. Then we flow, the next process is growing. So we flow methane or acetylene, it could be any of them. The precursor is flown to initiate the graphene which grows on the substrate. The argon and the hydrogen is supplied during the growth step. And as I said earlier, to improve the quality of the synthesized graphene, the parameters affecting the graphene growth, that means the growth temperature, the partial pressures of the hydrocarbon gas and the hydrogen, they are to be optimized. And of course, after a desired growth time, then we terminate the hydrocarbon supply and the system is cooled down before you unload the sample from the reactor. It has been reported, this is a very good paper, which talks about bridging the gap between reality and ideal in CVD deposition growth of graphene. So, although the process is known and it is established, it is not easy to get a large area growth of graphene, which is smooth, doesn't have wrinkle or contamination, and has the number of layers which are required by you. So the things which are required to be understood are the gas phase reactions which are happening there. So these are the important things. The mass transportation of the carbon precursor towards the substrate. And then these carbon precursors have to be adsorbed to form active carbon species. These active carbon species have to diffuse or dissolve, their dissolution into the bulk of the substrate has to take place. And then there is the initiation of the graphene nucleation by the on-surface collision among these diffusing carbon species or the segregation of the dissolved active carbon species. And that leads to the two-dimensional epitaxial growth of the graphene, where the graphene nuclei then merge to form a continuous graphene film. Of course, there's a possibility then you can dope the graphene also. We'll just have a look at that as well. So this is the standard procedure I'm talking about, which is the graphene growth by the low pressure CVD. chemical vapor deposition. So this is the ramping up step, then the annealing and the growth where the CH4 is introduced or acetylene is introduced, and a proper combination of the partial pressures of the hydrogen and CH4 and argon have to take place, and then of course the cooling down. So there are two mechanisms of the graphene growth on the substrate. One is the precipitated growth mechanism, which takes place when we have the substrate, for example, like nickel. So nickel has a tendency of forming a binary phase of metal carbide. And in this case, the decomposed carbon atoms, which comes from the precursor gas, they dissolve into the catalyst first and then precipitate to the metal surface to form the graphene. If we use a substrate like copper, then in that case, the diffusive mechanism takes place, where the decomposed carbon atoms, they do not dissolve. They remain or diffuse on the metal surface and then incorporate into the graphene directly. So the first mechanism, when we compare the two mechanisms, the growth in the second case is more uniform as compared to the first case. Because in the first case, there is a tendency of carbon segregating at the nickel grain boundaries, and that leads to a non-uniform multilayer formation. So this problem is taken care of in mechanism 2, and that gives the best of the synthesis of monolayer graphene. What does hydrogen do? The hydrogen, it maintains a balance between the production of the reactive hydrocarbonaceous radicals and the etching of the graphene layer during the CVD process. So if the ratio of methane to hydrogen is too low, that means the hydrogen is quite less, then the etching reaction, the hydrogen is more, then the etching reaction becomes much faster than the formation of the graphene layers. So it is like a double-edged sword. You can't make it like 2 more, you can't make it 2 less. So a very optimized hydrogen concentration needs to be there, hydrogen flow needs to be there to get the right amount of growth of graphene. So we can say that the hydrogen influences the uniformity of the graphene layers. This gives you that what is the role of substrate in CVD graphene formation. So there are 3 kinds of substrate, not 3 kinds. The material is the same, but their uniformity, the smoothness is different. Okay. Yes. And one thing is very important, that whenever you do some growth, whatever is the process you use, it could be chemical vapor deposition, it could be physical vapor deposition, the substrate needs to be clean completely with no contaminants. And in this case, it is very important, very critical, that how clean your substrate is. So there is an entire process of cleaning and etching the sample, the substrate, to make it ready for the graphene growth. And in this case, the authors have taken 3 substrates, okay, and where you can see that the microstructure is different. And when the graphene was grown on these 3 substrates, which they have named as copper 1, copper 2, and copper 3, you can see that the graphene growth is very much affected by the substrate smoothness. The intensity of the peaks is very different in all the 3 cases. So what this spectrum is, this is a Raman spectrum of graphene, which is like a method, we call it a fingerprint method to identify graphene. Okay. You can see that there are 3 peaks in this spectrum, D, G, and G dash, and we'll just have a look at what do they actually mean. Before that, This is the transfer process. So once you grow the graphene on a substrate, then you will have to, for its use, you will have to shift it to some other substrate. Okay. So this is your copper, this is the graphene below this. And then what we do is we take some polymer, which is usually PMMA, and then we press it, give some pressure and temperature to it. And then this copper substrate, the copper film is etched by using some etching agent. So what we are left with? We are left with the graphene on the polymer PMMA, which can be further resolved, uh, dissolved, and then you can transfer it to any suitable substrate you want, like silicon or wherever you want, even if freestanding you want. There is another method of graphene transfer, which is the electrochemical delamination process. So the growth of graphene is, as I said, it's typical, not very easy. At the same time, it transfer also is not an easy thing. And you really have to have practice and experience and optimize all the parameters to transfer it in a way that it does not get wrinkled. There are no, you are not doing any damage to your graphene film when you are transferring to the substrate you want. I think I'll come to this slide later. Let us talk about the Raman spectra of graphene. So if you look at the Raman spectra of graphene, there are three very important peaks. Okay, you can say the dominant peaks. Okay, the D, G, and 2D. Somewhere it is written as G dash also. Okay. So what are these bands representing? As I said, that Raman spectra is the most used method to identify a graphene or a carbon material, in fact, not only graphene. So the first band, the G band, it is gives you the sp2 hybridization, the presence of the sp2 hybridization in the graphene. It is highly sensitive to the number of layers which are present in the sample. So if you want to check that what is the number of layers which you've got in your sample, this is one method. Of course, we can use some other thing as well. So this is one method which determines the layer thickness just by observing the position of this band for a particular sample. The D band, it is known as the disorder or the defect band. It represents the ring breathing mode from the sp2 carbon rings. And this band is typically very weak in high quality graphene. So a high quality graphene will not have defects. So the D band would not be there. So if the D band is significant, it means that there are a lot of defects in the material. And 2D is the second order of D, although it does not represent the defect. Okay. And 2D band is always a strong band in graphene, even when there is no D band present. And this band is also used to determine the graphene layer thicknesses. So G and 2D, these are the two bands which we use to find out the thickness of the graphene layer or the number of layers there. And this is a study published in 2014 in Carbon, which gives you very clearly that how the intensity of the peaks is changing when the number of layers change. Okay. So this is the ratio I to D by IG. I to D by IG. Okay. And this ratio you can see for the number of layers. For 1, it is around 2.5 and reduces to about 0.5 when the number of layers is 3. So there is a sharp decrease in the ratio of these two intensities as the number of layers increase, and after that it shows an erratic behavior. This is a TEM picture, the transmission electron microscope picture, which can also give you an idea of the number of layers. So you can see that the number of layers in this case, you can see the increasing number of layers when we go from A to B to C to D to E to F. So you can very clearly see the number of layers in this graphene. This is a very good micrograph, TEM micrograph, to estimate the number of layers. And this gives you the set pattern showing the crystalline behavior of the manufactured graphene. So how these number of layers, they affect the property of the graphene. If you look at the conductivity, you can see that there is a decrease in conductivity when the number of layers increase, and there is a decrease in transmittance for large number of layers. So to get good electrical conductivity and good transmittance, especially as a transparent conductive thin film, you need to have a very few number of layers, especially less than 3, if you want to get good properties. This is the same image. Of course, you can see that the CVD graphene, it is broken. It is not continuous. So although in industries, they have, developed process for, large area growth of graphene. But in the research labs, still it is difficult to get large area growth of graphene, which is uniform. This is the Raman of the monolayer graphene, which one of my students who synthesized it. And you can see that I2D by Ig ratio is 2, which is quite good, and which just reflects that this is a monolayer graphene. This is the transmission electron microscope picture, the set pattern, not the micrograph. It is a set pattern showing the good crystalline behavior of this monolayer graphene. This is the micrograph. Although this is not very clear, this is a high resolution picture. If you look at the atomic force microscope of this monolayer graphene, in this picture, you will see, this is a really beautiful picture, that you can see the hexagonal arrangement of carbon atoms. So this was a high quality sub-monolayer, monolayer and bilayer graphene on RU0001 grown by these authors, paper published in 2014. And this is a very beautiful picture of a single layer graphene seen by the atomic force microscope. Now, because it is not very easy to use CVD for uniform growth and large area growth, and actually it is also not required to have a single layer graphene for all applications. So this is why mostly because of the inexpensive nature, the easy synthesis and availability of the fabrication devices, most of the researchers use the wet chemistry approach for the synthesis of graphene, which is not actually graphene, but the graphene oxide. And further reduction, we get reduced graphene oxide. So the typical procedure to form, to get the chemically synthesized graphene oxide, we just take graphite, okay? And this graphite, a three-dimensional graphite, it is then treated, or it is subjected to a severe oxidative treatment, okay? Using the sulfuric and the nitric acid. And as I said, the method was given by Hammers and Hoffman in 1958. And the Hammers method or the modified Hammers method are the two mostly used methods for the production of RGO. So this, then you have to go for the rapid evaporation of the intercalent at elevated temperatures, and then using the ultrasound or the ball milling, the exfoliation takes place. Then we go for from where we get the graphene oxide. In this graphene oxide, there will be large number of functional groups present there, and subsequent reduction of this exfoliated graphite oxide sheets by hydrazine or some other method, it gives you the reduced graphene oxide. Okay, the reduced graphene oxide is hydrophobic in nature. There are some other methods, as I said, the exfoliation or epitaxial growth on silicon carbide, but there the control is not good on the number of layers, and as I said, they are not very easy to fabricate methods. This is just the different steps which are included, taking the graphene's flakes, okay, using a strong oxidizing agent, continuous stirring, adding camenophore, and the various steps, and the centrifugation where we get geo, then the reducing agent is added, then the hydrothermal, and that gives you the reduced graphene oxide. Of course, the pH has to be maintained. The product is washed, filtered, and vacuum dried. This is the scanning electron microscope of the reduced graphene oxide. So you can see that these are the layers. These are the layers. So we have a large number of layers here, and they are wrinkled. They are not very smooth. So this is the usual what do you say, the morphology which we get in reduced graphene oxide. And this wrinkled morphology is useful in the sense that it gives it a very high surface area, making it useful for sensors and other applications. This is the Raman spectrum, and this gives you the Raman spectrum of both the graphene oxide and the reduced graphene oxide. So we see that the ID by Ig ratio, it varies when you get from, when you move from graphene to the reduced one. And in the case of reduced one, because the functional groups are less, that leads to, you can say, better hybridization of carbon, but at the same time, it may cause some defects also. So there is always a variation in the ID by Ig ratio when you go from graphene oxide to reduced graphene oxide. The FTIR again gives you the presence of the functional groups, and you can see that as we go from GO to RGO, because the functional groups are removed, here, this shows you the graphene oxide with the different functional groups, and these functional groups, not all of them are removed, but depending on the efficiency of your reducing agent, most of them will be removed, and that is why the intensity of the peaks decreases as we go from GO to RGO. This is the transmission electron microscope of the reduced graphene oxide. We have just seen the scanning electron microscope pictures for this RGO, and this is the transmission electron microscope. You can see that again it's a wrinkled film, and it has a very good transparency, but it is not uniform and smooth. And this gives you the polycrystalline nature. So what we did was we tried to find out the electrical transport properties of the RGO, and the Hall measurements we did using the 4-probe van der Waals method. And this RGO sample, it was, it made a solution, and it was drop casted on the glass substrate. The contacts were made using the silver paste, and the average conductivity came out to this value, 10 power 2 Siemens per meter, which is not a very good conductivity. Now, when we did the Hall measurements on the CVD graphene, that means the graphene which we grew using the CVD, then what we found was, we found the conductivity. You can see it is of the order of 10 to the power 4 Siemens per meter as compared to the conductivity 10 power 2 Siemens per meter. So a conductivity of 2 orders, there is an increase of 2 order conductivity in CVD graphene as compared to the RGO sample. And then the next step was to dope this graphene. We'll see just now that why the doping is important. So we introduced nitrogen during the growth process, and that led to the incorporation of nitrogen into the graphene which we were growing. And then there was a 1 order increase, about 1 order increase in the conductivity of graphene which was doped with nitrogen. So let us look at the applications of doped RGO. So in why the RGO was doped or the graphene was doped, because the conductivity, there were 2 things. One was that we could tune the band gap of these materials, and the other was that increase the conductivity. So electrochemical cells, supercapacitors, batteries, gas sensing devices, hydrogen storage, fuel cells, everywhere it was found that the doped RGO was giving better functionality as compared to the undoped RGO. So why doping? So as I told you just that this gives you band gap opening. So breaking the symmetry of the honeycomb structure. When we looked at the bonding initially in the initial stages of this lecture, so there was a honeycomb structure, and this honeycomb structure is broken, the symmetry is broken, so that leads to the band gap opening. So we can do by 2 methods. We can do some chemical engineering to break the symmetry and open the band gap, or we can use some physical engineering, that means some physical method to open this band gap. Okay. So we use the method of chemical engineering, that means doping. And again, depending on the type of dopant, you can you can make the material p-type, or you can make the material n-type. So what we did was, we did both the processes. We added a dopant in the process of the synthesis of reduced graphene oxide and doped it. At the same time, in the CVD graphene also, we introduced nitrogen gas during the synthesis and doped it. So both the RGO and the CVD graphene, they were doped with dopants. And this shows you the SEM image and the EDS mapping of the nitrogen doped RGO. So this is the different elements, and this represents the distribution of nitrogen. Okay, this is your carbon, this is the nitrogen, this is the elemental mapping which we get from the EDS, which is like added to the scanning electron microscope, and this is the presence of oxygen there. So you can see that there is a almost uniform distribution of nitrogen in the sample. This is the EDS mapping and SEM image of boron doped RGO. And this is the presence of boron in the sample. So why we were doing this? We were developing these materials as electrode materials for the supercapacitor. And then we tried to have a look at that by having asymmetric supercapacitors. That means one of the electrode as boron doped and the other as nitrogen doped, whether it was giving us good electrochemical properties. So that was the motivation behind it. And this gives the XRD, and you can see that with the presence of nitrogen in the RGO, the XRD peak is shifting. This is for all 4, the XRD peak of GO, RGO, nitrogen doped RGO, and boron doped RGO. And this is the XPS of which one? This is for nitrogen doped CVD graphene. So in the nitrogen doped CVD graphene, actually, the nitrogen incorporated into the graphene was not much. And to confirm the presence of nitrogen there, we did the XPS. And this is the XPS C1s spectra. And this is the carbon spectra for the CVD-NG. That means the graphene, which is doped with nitrogen, synthesized by CVD. And this is the nitrogen spectra. So when we deconvoluted both these spectra, we could very easily confirm. So when you look at this nitrogen spectra, you will see what happens, that the nitrogen in the graphene, when it goes at various positions, different positions, then that gives you either pyrrolic end, graphitic end, or pyridinic end. Okay. So deconvoluting this spectra, we could find the presence of all three types of nitrogen which are there. And then we could really explain the modified electrochemical properties of a sample using this. So this is these are the various plots of this doped graphene, which we tried to use as electrodes in a supercapacitor. So what we did was we compared the nitrogen doped graphene without doping graphene. And what we could find out was that there was an increase in a significant increase in the aerial capacitance. You can see very clearly, these are the CV plots of the CVD graphene. These are the CV plots of the nitrogen doped graphene. So you can see that there is a bigger area of the plots, and this gives you the voltage curves for the undoped and the doped graphene. So what we see here is that the aerial capacitance increases significantly. There is a slight increase in the energy density, with the power density remaining the same. Of course, the amount of dopant which goes into the sample, that also has to be optimized, and we still have to do that. Like this is still work which is not completed yet. That what is the amount of dopant which will give us the best properties. So people have used this process of doping graphene for the solar cells as well. And it has been seen that, these are the perovskite cells, and people have used graphene quantum dots, made their composites. And it is seen that if we use graphene quantum dots and nitrogen doped graphene and make their composite with polymer, then there is an increase in the current as well as in the performance. This is the case of the devices in dark. This is the first case of electron only, and this is the case of hole only. And these measurements have been done in dark. So there is an increase in current. You can see that for hole only, there's an appreciable increase in current, whereas for electron only, there is an increase in current after a certain voltage. Not initially. Initially, it is less. Then after a certain voltage, it increases. But overall behavior with the nitrogen doping is an improvement or a superior performance. This is also a comparison of then how the supercapacitor can be developed as a high performance supercapacitor just by having three-dimensional nitrogen doped graphene. Okay, so they have not only done the doping, they have also worked on architecture. And this is what actually people are doing, that they are not only incorporating different elements like making composites, but at the same time they are looking at that what are the, because for a supercapacitor electrode or a battery electrode, the morphology is very important, especially for batteries. You know, the ion intercalation and deintercalation. There has to be sufficient pore space or pore size so that the ion can easily move into and come out. And if it is not there, then the efficiency decreases. Also, if the ion remains there and during deintercalation, the efficiency is not there, doesn't come back, then it also leads to smaller life cycle, smaller life of the device. So, in addition to doping, people are also looking at controlling the architecture of the electrode, and this is where the three-dimensional materials are becoming very important. So in this case, they have made it a nitrogen doped graphene as well as its 3 dimension. And that again shows the increase in the current density on the specific capacitance. So the electrochemical properties, they improve appreciably on doping and having a superior architecture. So these are the references which have been used for this lecture. And this is what I wanted to convey. This is all from my side. If you have any questions, please let me know.
Thank you so much, ma'am. Dear participants, if you are having any query, you can directly ask to the expert or you can write down in the chat box, please. Other participants are requested to mute their mic meanwhile. Ma'am, there is a one query. What about the effect of coupling graphene with polymers in energy storage systems?
Can I speak to the participant directly?
In the chat box, one of the participants have asked, what about the effect of coupling graphene with polymers in energy storage systems?
Okay. So, first of all, we couple polymer with RGO, as I said, not with graphene. Okay. It is difficult to, graphene is a single monolayer. Okay. It's a single layer. When we talk about composites, we normally use is the RGO or GO. Okay. And RGO and GO with polymers have already been proved to be more effective, having more superior properties in almost all applications. You have to choose the right type of polymer for that.
Okay. Dr. Pankaj Kumar Singh, you can unmute your mic to ask the question. Dr. Pankaj Kumar Singh, you have raised the hand. You can unmute your mic to. Or you can write down in the chat box.
Madam, I have a question.
Yeah.
Regarding the growing graphene on copper. So, what specifically makes copper or nickel suitable for graphene growing, in terms of melting point or some absorption?
No. They're chemical properties because they act as catalysts.
Okay.
Hello, ma'am. Am I audible?
Your sound is very low. Please
Speak loudly, please.
What about now, ma'am? Is it audible?
It is audible, but थोड़ा आप जोर से बोलो. आवाज
ma'am.
कम आ रही है.
Okay, ma'am. I'm a research scholar who is.
Now it's better.
I am working in the same field. I am working on supercapacitor, the development of some electrodes. So my work is mainly focused on reduced graphene oxide system. So during the preparation of this graphene, I am using the modified torque group. Can you say which is the better method for the preparation of reduced graphene oxide, if it is torque group method or any other hammers like method? Can you?
Which you have been using, that comes by experience. People, there are about 100 methods which the people are using. Fine.
Okay, I'm using the modified torque group method.
Okay. And is there any problem you are finding there?
Okay, the main problem is that when I reduced to the reduced graphene oxide, the product is that much. What I want to say that the properties are something different when compared with the pure form of that reduced graphene oxide. That's why I'm asking the same.
Okay, but we are using modified Hammers method. You can try that.
Okay.
Because I have
Modified
not
it.
tried all the methods, so that's why I cannot comment on them.
Okay.
But we are using modified Hammers method and we find it.
Okay. Thank you, ma'am.
Okay, ma'am. There is a question from Mr. Naresh Babu. To determine the stability of graphene nanoparticles be dispersed with canola oil, can I use UV visible spectrophotometer?
UV visible spectrophotometer for?
To determine the stability of graphene nanoparticles dispersed with canola oil.
No, UV visible will not give you stability. That just gives you the optical properties.
Yes, ma'am.
Yeah.
Any other
I'm basically not a chemist. So I'm a physics person.
Yes, ma'am.
So what happens in canola oil, I'm actually not knowing. So I cannot comment on that, but I can tell you that UV visible gives you the optical properties. That will not give you stability.
Yes. Any other participants, any query? Ask directly or you can write down in the chat box. Okay, in case of no further query, thank you so much, ma'am. I thank you on the behalf of the organizing committee, our college, and myself personally for joining this session and sparing your time with us and giving us so brilliant lecture about the graphene and its role in the energy conservation.
Thank you, Dr. Sanju. Thank you for giving me the opportunity to share my work with the participants. I hope they found it useful.
Of course, ma'am. Thank you so much,
Excuse
ma'am.
me, ma'am. Hello, ma'am.
Yeah.
Yes.
I have one more question regarding this, not related to this topic. Are you able to give some clarifications regarding carbon nanotubes?
Carbon nanotubes, I have not worked much.
Okay.
What is your question? If I
Okay,
can
ma'am.
just.
I wish to use instead of this graphene oxide, I wish to choose
Mhm.
this CNT for making the electrode materials for the highly high efficient supercapacitors.
Yes, they would be more useful because they have more conductivity. They have better conductivity.
But
The only
the
thing is, yes.
when I search when I'm going through the literature search with the number of journals or the periodicals related to this work is that much low. If it is related, why it is so? Maybe it is due to the dispersion capability, low dispersion capability of
Yes,
CNT.
I was coming to that. It's better to use a composite, because
Yeah,
RGO will give you flakes. Fine.
yeah.
And RGO gives you flakes, and CNT is like jumbled up, so many carbon nanotubes, all jumbled up. So
Okay,
when the agglomeration is there, then the properties degenerate. So it's better to use a combination of them, and so you will get conductivity from CNT and a better surface area from GEO or
okay.
RGO.
Okay, one more doubt. I used to prepare this modified Tor group method for the synthesis of graphene oxide. One more my doubt is how what about the stability of this produced or the prepared graphene oxide if it is urgently required to convert it to the reduced form, or if any oxidation reduction will be happen automatically for that particular graphene oxide?
No, it doesn't happen automatically.
Okay,
It
it's
is
only be
stable. Geo
taken
is quite
the
stable.
process of.
Yes.
Okay, GO is stable, but most of the
Yes.
works is mainly for the reduced state. Why it is?
Because Geo doesn't give you electric conductivity.
Oh, that's why most of
Yeah.
them is
Because
reduced
there are
to.
so many functional groups, doesn't give you
Yeah.
electrical conductivity. So you have reduced those functional groups to get the electrical conductivity.
Okay. Thank you, ma'am. You give a nice lecture for me, and I got some clear points regarding my research. Maybe these points will be helpful for my work. Thank you once again, ma'am.
Thank you.
It's a word from my bottom of heart because that much useful lecture. This is from my side. Thanks. Okay. Thank you.
I got it. Thank you.
Okay, participants, any other wants to ask anything? Okay, ma'am. Thank you so much for the session.
Can I leave now?
Yes, yes, ma'am, surely. Thank you so much.
Okay.
Okay, so to all the participants, next session we are going to start from 12 p.m.